now that I'm not inflation. Okay, where were we? Atwood machines. Okay. Let's do 30. Get a nice answer for that one, and then we'll talk about the pushing or sliding the. I call this the broom problem, because I know it's a block. A block would not be a very good broom, but I mean everything's a block, really, if you think about it. It's kind of like, it's like how a coffee mug is a donut, right, Julia? You know what I'm talking about?
I don't.
You feel me? They say that to a topologist, a coffee mug is a donut, because look at a coffee mug. How many holes does a coffee mug have? Well, assuming you have a handle. So you got this mug, right?
Whoa.
Now, if you think that this is a hole, that's not a hole, because that's just a divot. I can make a really crappy coffee cup where this is just like a very gentle little like divot. So anyway, topologically, a coffee mug and a donut are the same shape. They both have one hole. So, and a straw. A straw also is a donut. So a straw has one hole, right?
Mr. Paul, you buy a coffee shop and you serve coffee cups in just like 2 hours.
Yeah, the Nespresso, where it's a big solid mug and it's a little tiny like indentation in the top, and that's what the espresso
Charge
says.
$4 for it. Yeah.
In Portland, that might be successful.
Then you give them a metal straw.
Yeah, there you can use a metal straw or bamboo straw. Okay, so number 30.
Okay, just let me know. I will just.
So M1 and M2. This is theta. And we continue our journey of trying to be able to write a general equation for a system, right? It's probably the hardest part of a class like this, is getting your mind in that mindset of setting it up as you would do with numbers, but where instead of every number, it's a symbol, like an M1 or M2. Okay? So this is frictionless. So not to be confused with the friction problems we did. Colin, what's going on back there? Colin, what's going on back there? Listen to this. Oh, okay. Very good. Okay, so look at this system. What's the system of equations? So how much force is there pulling this thing down? M2G. Okay, how much is pulling it up? Some tension. We don't know the tension yet. How about this one? Tension. And this. Hopefully we're M1G, the gravity force, times the sine of my angle. Now, if there was friction, you would also have to consider the normal force, which is M1G cosine of theta times whatever mu, but there's no friction in this problem, so that's nice. Okay, it says write an equation for the acceleration of the system. So you gotta set up a system where you're gonna write F net equals MA. All right. Which one should we do first? Sure, let's do this one first. So it's going to be F net. Now here's the thing. We're not really sure what direction it's going to go. Because if this was much, much heavier than this, it would certainly go this way. So we have to just arbitrarily decide, I don't know, let's make this the positive direction. All right? So this is positive. M2G minus T. And what goes here?
M2.
M2 times A. Now how about this guy?
T minus.
There we go. Everyone okay with that? Now, these are pretty complicated formulas, but the nice thing is that I hope you recognize is structurally, this is identical to a problem we've already done involving numbers. So it's not, as long as you don't freak out, you're like, oh, it's the same exact process, okay? We just got these little scary subscripts and extra letters. Scary. Okay, add up this and this. What do you get?
You get M2G minus M2G.
Yep, so you get this, the minus t and the plus t cancel out, you get this minus this. Let's add these up. Okay, now the question's asking us to solve for, we're solving for what letter? Acceleration. So let's factor out the A. I'm also just for aesthetic purposes, writing it as M1 plus M2 rather than M2 plus M1. You don't necessarily have to do that, but could I also factor out something over here? Factor out the G, because then down the road, it's going to be nice to be able to have everything in terms of G as some ratio. So there you go. And then we're done. So A is equal to G multiplied by some factor. And that factor is this ratio M2 minus M1 sine theta over the sum of M1 and M2. The second half of the question is actually pretty easy. That's easy. Okay, so then part B says what condition is necessary for the system to remain at rest? So the at rest condition, can I write it really simply? Is there a simple way to write it?
I just put their gravitational forces have to cancel each other out.
Yeah, this would have to equal this, right? You could set the acceleration equal to 0 and then do a substitution if you want. If you're thinking really, wants to be really mathematical, but I would argue this is just as mathematical to say if this force and this force are the same size, then the system won't move. And so I could say M2G has to equal M1G sine theta. Okay. By the way, this gives you an interesting result if you think about this. What is a scenario? Maybe someone can get this one. This is kind of a read my mind scenario, not the best question to ask, but what's a scenario, kind of the trivial scenario where this would remain at rest that you can see borne out in this equation?
Because well, the G
If theta was 0,
of gravity.
If theta was 0, it would be this scenario.
oh, okay. That would not work.
Although the scenario I'm thinking of would still have no acceleration even if theta was 0, even if the ramp had no slant to it, which would be, hint, hint.
No breath.
Yes, what if G was 0? Right? What if you were in deep outer space, or if you were in orbit? Say you're on the ISS, right? If G were 0, right, this equation would read 0 equals 0. So what the trivial solution to this would be, what if there was no gravity? Then there would be no acceleration, right? No, did I lose you? Does that make sense or no?
That makes sense.
Kate? Maybe? Okay, sorry. Okay, so now can we get this to look a little bit nicer? What's a nice way to write this? Cancel out the G's. So assuming G isn't 0, then it doesn't matter what number it is. So G could be 0, but if G's not 0, I could divide both sides by it, and then I could write this really nice equation. We love this stuff in physics, is relationships like, if the ratio between the masses is equal to the sine of the incline angle, then the system will be in equilibrium. Okay. Okay. Let's do the broom. The broom.
I was doing like flow. International Space Station in my dream.
Yeah.
Yeah.
What were you cloning?
Humans, of course.
Oh, humans. Wow. Jeez.
Okay.
Okay.
It was really weird. Wacky.
There's an interesting movie with Arnold Schwarzenegger where it's like in the future and they have technology for cloning pets. And there's like a business, you go to the mall and you can get your pet cloned. Like if your pet were to pass away, you could go get it cloned. That's when the movie starts. Arnold Schwarzenegger, his kids, like I think it's like their dog or their cat passes away. So he's like, oh, and his kids are going to be upset. So he goes and before they find out, he goes to the mall.
It's like a remix of Pet Cemetery.
No, they're like in an Indian burial ground, aren't they in the movie? No, in this movie, he goes to the mall. It's like a business, like a glossy business. They go, oh, just bring us any sort of DNA sample from your pet and we'll create a perfect clone of it. Anyway, so of course it's a sci-fi movie. So it is revealed to Arnold Schwarzenegger that they actually, through a bunch of events, actually they can clone humans and they're all over the place. I can't remember the name of the movie though. I think it might be called like Clones. Clones, the movie. Yeah, that's what it's called. Anyway, if you looked it up, you'd find it. Arnold Schwarzenegger clone movie. It's a little cheesy, but it's kind of interesting idea. Okay, so 32. I call it kind of the room problem because this is a 10 kilogram block, and it is being. What direction is it being? Having force exerted on it. It's being pulled to the right at this funny angle here. So this, and it says it's being pulled with 100 newtons of force. Okay? So that's all we know so far. So this is 30 degrees, according to the problem. And then there's friction between the floor and the block, where mu is 0.4. Okay. So you guys have all pushed a broom. Maybe you haven't pushed one of those big Swiffer sweepers. When is it harder to push it? When you're pushing it or when you're pulling it back? It's harder? That's the opposite of the answer I thought you were going to say. I would say when you're pushing it, when you're cleaning the floor, when you're pushing it forward, you can feel there's more resistance. There's more force is required.
Oh, if you're trying to exert more force by pulling it back, then it's hard.
Oh, because then you're having to
Yeah.
I get what you're saying. With like the geometry of your body, it seems like you're putting in more effort. Yeah. So anyway, for this problem, maybe then don't think of it like a Swiffer sweeper because you might get flipped around in your head. But so that's the force diagram. The question is, we're going to answer what's the normal force on the block by the floor, what's the friction force, what's the net force, and what's the acceleration. So we're going to just get all the big four things. So first, let's draw a force diagram. So this is one force. How many other forces are there? You got first there's gravity, right? This is 98 newtons, right? Then there's the normal force. So gravity pulls the block down, and then the floor, notice the vector I'm drawing is kind of short. Normal force. Now, why did I draw that vector so short?
Because of the angle which
Because that,
Well, this vector does two things, right? It pushes the block to the right, but it also lifts the block. So what has to be true about these two vertical vectors? No. Is the block going up or down? They have to add up to 98. Everyone okay with that?
Yeah.
Okay, so let's break up this vector. So use it right here. How do I figure out the horizontal component?
But there's a huge cosine. Sine.
It would be the hypotenuse is 100, and I multiply it by the. What do you guys think? Sine or cosine to get the horizontal?
Cosine.
Oh, guys. Guys, don't forget the basics. The basics is this. If the vector is some force F and this is theta, the horizontal component would be F cosine of theta. This would be F sine of theta. So make sure you remember that. This is kind of the core idea of everything we're doing here. Is that using some basic trig, you can break up any vector into two perpendicular components. Most of the time it's a horizontal and a vertical. Okay? So in this problem, my x component would be 100 times the cosine of 30, which I think this is one I know. Can someone confirm this with the calculator? It's 86.6.
Yeah.
And then the y component, the vertical component, would be 100 times the sine of 30, which is, and that's one I definitely know, it's 50, because sine of 30 is 0.5. So these two numbers are really important. Okay? Wait, so how big is this going to be? I think you got 38, right? No, 48. No, you're right. I'm sorry. I was wrong. 48. Sorry, 48. You're right. 48. So does everyone understand why, like, I can write something like the normal force plus this vertical force plus this 50? I might call this the lift. How much I'm lifting the block has to balance out with this 98. Therefore, the normal force has to be 48 newtons. Do we all understand that? Stop me now if you're confused. So the answer, so we've already answered A. That's a complete force diagram. Okay. I've got the normal force from the floor, the gravity force from the earth, and the pulling force from the handle, the rod. I've just calculated the normal force. Okay, so let's now get one more force on our force diagram. So as we move down here, we got to go, well, that's actually not the entire picture, is it? Because this block should be moving to the right. So there's going to be a friction force right here. Everyone okay with that?
Yeah.
Now let's calculate that. Formula for friction force.
MK times that.
Mu, right? So mu times the normal force. Good. So for in this particular situation, our mu is 0.4, and our normal force is
48.
So hopefully you're thinking about what this means. The more force I exert here, right? The more vertical force I provide, the less normal force there is, right? Which means there's less friction force, which should hopefully agree with your intuition on this, right? The more I kind of pick the thing up off the ground, the more I exert upward force, that's going to alleviate some of that friction. Conversely, if I push down on it, it's going to increase the normal force and increase the friction. So what is this? What is this? Okay. 19.2 newtons. Very good. So that's part C. How about the net force? It's actually easier than you think. Now, there's a lot of stuff up here. Not easy, but the net force is actually pretty simple.
Would it just be the force X minus the friction force?
Yes. So for part C, let's get this set up. I'm going to write F net equals MA. We're going to get two questions at once here. F net, since the vertical forces balance out, to get the net force, I just have to look at the horizontal forces. So there's 86.6 pointing to the right and 19.2 pointing to the left. So my net force is 86.6 minus 19.2. So this value here, whatever that is the net force. And then set it equal to MA, and you'll get the acceleration. That's 67.4.
Yeah.
So 67.4. That is the normal force, that many newtons. and the acceleration is 6.74 meters per second squared. Yay! Fun. What, Julia, question?
Nope.
No.